Hello, everyone. My name is Melissa Davis, and Professor Kurt has asked me to fill in for him and do the chapter 19, which is on weather patterns and severe storms. I did get my bachelor's and master's degrees from IU in meteorology, so this is what I love, and I especially love severe storms. I've never seen a tornado, but that is a lifelong dream of mine. Now, I don't really want to see it coming directly at me or at directly at my house, but somewhere off in a cornfield or a wheat field where nobody gets hurt, but I just want to see it. Anyway, so thanks for joining us today, and let's get started on chapter 19. All right, so we can first start with air masses, and air masses are large bodies of air. I mean, really large, like maybe 1,000 miles or even greater across. And they can also be several kilometers thick. So they're wide and they're tall. And what makes an air mass is the temperature and the moisture content of these big piles of air are very, very similar. So, maybe you have a large swath of air that has a pretty high relative humidity, but it's also cool. And so that would be a moist, cold air mass, obviously. Now, these air masses form over different regions, and that's where they pick up their characteristics. And we'll talk about the source regions in just a moment. But as these air masses start to move, they carry those characteristics with them. So if it starts out cold and dry and it moves into an area that is warmer with greater humidity, as that air mass moves through that area, you would expect the temperature to drop and the humidity to drop a little bit. So that's what this is showing. So here we have a cold, dry air mass. And I mean, this is very, very cold, minus 51 degrees Fahrenheit. I don't need to ever experience that. I'm good. I'd rather experience a tornado. So this cold, dry air mass has developed in northern Canada, and then it starts to move. And as it moves southward, it's going to bring a blast of colder, drier air wherever it goes. So as you can see, it started off at negative 51 degrees Fahrenheit. By the time it hit Winnipeg, it was minus 27 degrees. And by the time it got to Oklahoma City, it was at 5 degrees Fahrenheit. And if we go all the way down to Tampico, Mexico, it's 50 degrees. Now, 50 degrees doesn't sound too bad to us, especially, like right now, this time of year. But for Tampico, Mexico, which is in the tropics, that's very cold for them. So, temperature is a relative idea a lot of times, where what's cold to one is not cold to another, and so on. But regardless, even though the temperature has warmed up significantly, it's still bringing a blast of cold air to the places where it moves across. Okay, so here's where we can talk about source regions. And source regions, as I said, this is just where the air mass picks up its qualities of temperature and moisture. Now, we can define air masses based on their source region, and we do that with a combination of letters. So we can have polar air masses. Polar air masses obviously come from a high latitude. So this is, maybe 50 degrees north and 50 degrees south to the poles on either end. And with this forming in the high latitudes, you can expect that it's going to be cold. Now, if it forms in the winter, it's going to be extremely cold, like the example we looked at. However, if it forms in the middle of the summer, it's still going to be cold, but it's going to be relatively cold. So, you know, this might, for instance, here in Indiana in the middle of July, if a polar air mass moves into our area, we might see a high of 72 degrees Fahrenheit instead of a high of 92 degrees. Okay, and then we have tropical. So tropical air masses, as you've guessed, come from the lower latitudes where it's warmer. So again, if this moves into our area in the winter, it's going to bring a nice change, bring some warmer air. So maybe it gets up to 50 or 60 in the middle of winter, and that's always a welcome thing. So polar and tropical both indicate the temperature of the air mass based on where it was formed. Now the next part, we have continental, and continental forms over land. Because it forms over land, land is mostly dry. So the relative humidity of this continental air mass is going to be pretty low. The opposite of that is maritime. Maritime air masses form over water, so over the oceans typically. And as you might have guessed, we would expect those to be pretty humid. So these, the first two, the polar and the tropical, indicate the temperature of the air mass, and the continental and the maritime indicate the humidity or the moisture content of the air masses. So there are four basic types of air masses. At least these are the ones that affect the US most often. And it's a combination of these classifications of temperature and type of terrain that they form over. So the continental polar, okay, that is abbreviated with a lowercase c for continental and an uppercase p for polar. So that means that it is dry, we get that from the continental part, and cold, p, from the polar part. So continental polar air masses, again, these are air masses that will move southward from Canada. And in the winter, we get the frigid temperatures, and in the summer, we get some nice relief. Continental tropical. So continental, we're still talking about a dry air mass, but tropical, now we're talking about a warm and dry air mass. So this forms over over a warm, dry area. In the US, most of these continental tropical, these dry, hot air masses form over the center of Mexico, and they will move northward. Maritime polar, maritime meaning that it has formed over the ocean, over water, so it's going to be fairly humid, and polar is, again, cool. So a maritime polar air mass, it's going to be cool and very damp. So, you know, a really good example of this is, think about Seattle or the Pacific Northwest, where it's just always kind of really damp and cool. Maritime tropical. So we get a lot of maritime tropical air masses here in Indiana. Maritime, it comes from over water. Tropical meaning it's hot. So we see the maritime tropical air masses most often here in the summer. And this is why it's so humid here in Bloomington in the summer. This air mass is coming from most likely the Gulf of Mexico. So when the Gulf of Mexico warms up, it forms an air mass that's hot and very humid, and then it starts to move northward. And that's, you know, when we have the relentless heat high humidity, and frankly, it's just too hot. Okay, so what we're looking at here are the air mass source regions for North America. All right, so we have continental polar, which is cold and dry. So they're showing where it forms, where its source region is, and the direction that it typically moves, okay? Maritime polar, this is cool and humid. Okay, this forms over water, and this is typically colder water over here, and then it moves inland. So this is why the Pacific Northwest has such cool rainy weather. We also have another maritime polar source region over here in the North Atlantic, and that can either move south-southwest, or it can move more east-southeast. And this often will affect the New England states. Maritime tropical, this top diagram is for the North American winter. So maritime tropical, this is a warmer part of the ocean. So for this, we're going to get the warm, humid air, and that's going to move toward Baja California. Another maritime tropical here in the Caribbean, Gulf of Mexico, that's going to move north, but it doesn't often really penetrate into the northern part of the US. The jet stream kind of keeps it a little bit south. The bottom, the top pattern up here, we didn't talk about this type, but this little bubble right here is continental Arctic. Arctic is colder than polar. So luckily, this continental Arctic, this very cold, very dry air, typically stays up in Canada, in northern Canada, where they like it up there. But sometimes it will slide south, and sometimes it will invade our area here in Indiana. And those are the times when we get the temperatures well below zero. Thankfully, that doesn't happen all that often, but that's where it comes from. Now in the bottom diagram, this is the summer pattern, and you can see that some of these have shifted just a little bit, and they'll shift with the seasons. So the first thing you can notice is that the continental Arctic air mass that we had in the winter is gone because, you know, we've warmed up enough. But we can still get cool, dry air coming from Canada. We also have the maritime polar, cool and humid over here. Maritime tropical, as you can see, this has moved northward a little bit, so it's affecting a greater area of the West Coast. Maritime tropical, about the same area, but now it's able to move much farther north. As you can see, Indiana is right there. So that's when we get our really hot, really humid, sticky summer days. And right here over central Mexico is the continental tropical air. This continental tropical air is hot and dry, and it doesn't often move from its source region, but sometimes it will move a little bit north. Now, the one thing I'd like for you to notice is that we've got the continental polar air mass moving down this way, maritime tropical moving this way, and the continental tropical moving this way. And they all kind of meet right here in the center of our country. Can anybody tell, well, you're not going to tell me because I'm not live, but can you think about what is common in the central part of the US that has to do with weather? Can you think? All right, so the answer is, this is Tornado Alley. And that's the reason why, because we've got a temperature difference, a temperature gradient, and we've also got a humidity gradient. And those are the things that come together to help form severe storms and often tornadoes. And we'll talk about tornadoes later today. All right, so we've already kind of done this, but we'll go over it again. So North America, and we're talking about, in this case, east of the Rocky Mountains, because the mountains do have an effect on the weather. East of the Rockies, the continental polar and the maritime tropical air masses are the most dominant, whereas the continental polar air mass comes from northern Canada in the interior of Alaska. In winter, it brings the cold, dry air, and in summer, it's a nice, nice relief. Oops, sorry. As this air mass crosses the Great Lakes, if the Great Lakes haven't frozen over yet, then it's able to pick up a lot of that moisture. What happens is it picks up this moisture and gets completely saturated. The temperature goes up a little bit, and then by the time it gets to the other side of the lakes, the temperature is colder. And as you've learned in a previous chapter, cold air cannot hold as much moisture as warm air. So it has to dump this excess moisture, and it dumps it as snow, and that's what's called lake effect snow. So I'm gonna kind of attempt to draw this for you here. Okay, so what we've got is right here, this is land, and this is our water, Great Lakes. Okay, the wind is moving in this direction. Now this air right here is cold, but as it moves over the warmer lakes, because remember the lakes have not frozen over yet, as it moves over the lakes, the air warms up a little bit. As it warms up, it's able to pick up that moisture. It can evaporate some of that moisture from the warmer lake into it, and so the air mass warms up a little bit. So now it's a little bit warmer, and it's holding a lot of water, and oftentimes it is saturated with water. As it moves over the land on the leeward side of the lake, the air is much, much colder. And so cold air cannot hold as much moisture. So it's got all this moisture that it can't hold on to anymore, so it dumps it. And so what we end up getting, these are snowflakes. I know it's not very good, but it snows right here and it just dumps it right there. So they often get, 2 feet, 3 feet, 6 feet overnight. And that's because the lakes have not frozen over and it's picking up that moisture. Another way to think about going back to the fact that warm air can hold more moisture than cold air, let's talk about beer. Okay, so this is our mug. Okay, and then over here we have a shot glass. All right. As the colder air moves over the lakes, it warms up a bit. And as it warms up, its capacity to hold moisture increases. So let's say that this is moving over the lake and it gets completely saturated. Okay, so you're filling your beer mug up completely. Okay, it's almost to the very, very top. So this would be a relative humidity of 100%. Okay. Now, when we get to the other side of the lake, over land, the air is much colder. And remember that colder air cannot hold as much moisture as warmer air. So this beer mug is completely full. Now what happens if you pour this beer into the shot glass? Well, it's going to overflow, right? Now, why would you do that? Why would you waste beer like that? But it's going to overflow because this cannot hold as much as this. And so that's what happens. You get spillage. And in the case of lake effect snow, that spillage is the snowfall on the other side. Okay. All right, so here's a much better depiction of lake effect snow. So over here, we've got the cold, dry air mass. It's moving over Lake Superior that is not yet frozen. As it's going over, it's picking up that moisture. It's warming up a little bit, becomes saturated. As it reaches the other side of the lake, where again, it is colder and drier, it cannot hold on to all that moisture. So it just dumps it in the form of snowfall. Okay, so again, we're still east of the Rockies. The maritime tropical air masses again come typically from the Gulf of Mexico and the Atlantic Ocean. This brings warm, moist, unstable air, and it brings precipitation to the eastern part of the US. The continental tropical, this is what forms over the Southwest and Mexico, and it's hot and dry, and it doesn't often move outside of the source region, but sometimes it does. Maritime polar, this is cool and humid. This is what brings precipitation to the western mountains, the Cascades, the Sierra Nevada, and the western side of the Rocky Mountains. Now, sometimes remember that the maritime polar air mass can also be found off the northeastern coast of the US. And so sometimes this will cause a nor'easter. You may have heard that term before in New England, with cold temperatures and snow. And so a nor'easter, it's just what they've named these types of storms that move up and down the New England coast, basically. And they often bring a lot of snowfall with it. Here's air mass modification. We've already kind of touched on this, where you've got cold, dry, stable air, and I believe this is Siberia. And as it moves, it does get modified a little bit as it interacts with the surface below it. So it's still right here considered a continental polar air mass, but it's not quite as cold and it's not quite as dry. Then, if it continues over the open ocean, it's no longer going to be classified as a continental air mass, because now it's a maritime air mass. It has increased its moisture content. Okay, so you've probably heard the meteorologist on TV or whatever talk about fronts. And fronts are just boundaries that are separating air masses of different densities or different temperatures because of different temperatures and moisture. So for the most part, air masses retain their identities. If they're cold and dry to start off with, they typically remain cold and dry, at least as long as they're over the same type of surface. But they will collide with other types of air masses. When they collide, whichever air mass is warmer is also less dense, which means that it's going to be forced upward. Warm air rises. So the cooler, denser air acts as a wedge underneath. The cooler air kind of undercuts that warmer, moister air and pushes it upward. So we can look at it in this way. So this is our cold front, and this is our warm air. Okay, the cold front is moving in this direction. So that's what these triangles mean, that they indicate the direction of movement. So this cold, dry, dense air mass is moving into a region where it's warmer and moister. This cold air, because it's more dense, it's going to tend to be down closer to the ground, and the warm air is a little bit, rises just a bit. Now this cold air, it undercuts and it bulldozes kind of right underneath that. And so what happens is right in front of the cold front, we have air rising, and it's rising. It can oftentimes rise a lot to the top of the troposphere. So right here in front of the cold front is where we would see, let's see if I can draw a thunderstorm. Yeah, there we go, thunderstorm. And that's also where we might find tornadoes, just in that area in front of the cold front, because this air is being lifted. If it's unstable, we're getting condensation, latent heat release. And again, we'll talk about thunderstorms a little bit later. A warm front is the opposite. So let's do this. Okay, so well, this is really kind of bad. All right, maybe I won't try to draw that. Okay, a warm front means that a warm air mass is moving into an area that's colder. So the warm air is replacing the cooler air. And we denote that on a map with a red line and semicircles. So my line isn't red, but you can imagine that. And so these are the semicircles. And again, this indicates the direction of movement. Now, the slope on this is much smaller. So it takes 2 to 3 days for a warm front to pass over an area, whereas a cold front can move through in a matter of an hour. So let's see, let's do it this way. Okay, so this is the ground right here, and here's our warm front. So warm behind here, cold there. Now the warm air is not dense or heavy enough to move the cold air out of the way. The cold air is really dense. So it's not strong enough to push it out of the way. So as it advances, what it has to do is ride up over the top of that cold air. So you can see signs that a warm front is moving through your area several days before it actually moves through at the surface. So the first day that a warm front is moving through your area, you might see some really high, wispy cirrus clouds. Okay, this is, day one. Okay. The next day, as this continues to move, the clouds get a little bit lower. So maybe cirrocumulus. So that's day 2. The next day, they get lower even. So altocumulus, altostratus. And then finally, maybe on the 4th day, you have completely overcast skies, low-hanging clouds, and you often get some steady precipitation with it. So it does take a number of days for this warm front to actually move through at the surface. So, but you can see it. So the first day you look up and you're like, oh, there's some cirrus clouds up there. I bet it's going to warm up soon. And the next day they get a little bit lower, and then voila, 4 days later, hey, temperature goes up. Oh, good, they've drawn it for me because I'm really not good at that. Okay, so here's our colder air. Here's our warmer air. It cannot push it out of the way, so it's going to rise up over the top. So the way they've drawn this, the actual ground portion of the warm front is back in Kansas City, but it is starting to move through Pittsburgh, which is quite a good distance east of Kansas City. And so in Pittsburgh, they're seeing the cirrus clouds. In Columbus, Ohio, they're seeing cirrostratus. They're a little bit lower in the sky. Here, oh, well, not here, but Indianapolis, the clouds are lower still, and we're getting some moderate precipitation. Okay, and then this whole thing just continues to move east. All right, so in a cold front, the cold air is replacing the warm air. The cold fronts move much more quickly, and cold fronts are typically associated with thunderstorms, severe thunderstorms, and tornadoes. With cold fronts, the intensity of the precipitation is greater. It's going to rain very, very heavily for a shorter period of time. Warm fronts, these are the days that are kind of washouts. It's just a steady, persistent, nasty rainfall throughout the entire day. Now, once a cold front moves through your area, you'll be in a colder air mass. And so the temperature will drop. The humidity typically drops. We get subsiding air. So now we have air that is falling. It is actually coming down instead of rising. And when air is sinking like that, you cannot get clouds forming, so you often have clear conditions. Many times after just a horrible night of storms, the areas that are hit hardest on the next day, they have beautiful weather, beautiful blue skies, low winds. It's just gorgeous. And that's because the cold front has moved through that area. All right, so here's our cold front. The cold air is moving this way. And remember, it's heavier, it's denser. It's going to move underneath that warmer, moister air, and it's going to shove it upwards. If you've ever shoveled your driveway after it has snowed, if you take the shovel and kind of just push it along the driveway, you know that the snow just piles up on the shovel. That's because you're coming underneath it and you're shoving it upward as it accumulates. That's the same thing that happens with this cold air. We can also have a stationary front, and a stationary front on a map looks something like this, where we've got alternating blue triangles and red semicircles. Gosh, I drew that absolutely backwards. I'm so sorry. So it should be like this. All right. Okay, so blue triangles, red semicircles. So down here we have warm air and we have cool air or cold air to the north of it. Now the reason it's stationary is neither one is really advancing on the other. They're just kind of flowing parallel to one another. They're just coexisting. Nobody's bothering anybody else. They just hang out. An occluded front happens when a cold front overtakes a warm front. And this typically indicates the end of a mid-latitude cyclone. So, you know, we've got the different stages of the mid-latitude cyclone where we have the warm air moving this way and the cold air moving this way because we've got a low pressure system. So the air around the low pressure system is moving counterclockwise. This cold front moves faster than this warm front. And so it's eventually going to catch up to it. And so what it would look like would be something like this, where this part is the occluded part. This is the occlusion. where the cold front has caught up to this part of the warm front and it's starting to pinch it off. It's almost like a zipper. And so in this occluded part, the cold air wedges the warm air upward. We can't always predict what the weather is going to do in this occluded part, but it kind of pinches off the precipitation and moves it, is forced upward. Oh, good, we've got pictures. Okay, so this is basically what I've drawn, but it's just a different perspective. So here's our cold air advancing through our warm air. We're pushing up this warm, moist air, and then the cold front catches up to the warm front right here, and we get heavy rain, but we're forcing this warm air north, or not north, upward. And then as that cold front continues advancing, it continues to pinch off that warmer air, and it's all of that warmer air is forced aloft, and we're left with kind of coolish air down at the surface. All right, I just mentioned mid-latitude cyclones, so let's look at those. Mid-latitude cyclones are really what bring us most of our weather here in the mid-latitudes, and we are considered a mid-latitude area. So this is an area of low pressure. If you've seen a weather map, you often see, the H's and the L's. This is an L. Okay, so this forms usually along a stationary front. So remember, our stationary front has warm air to the south and cold air to the north, and they're flowing parallel to one another. And this cold air is often continental polar, and the warm air is often maritime tropical. Okay. Now, for whatever reason, one of those starts to advance on the other one. Okay, so what we end up with is we start to see, we no longer have a stationary front because now it's moving. So we start to see the warm air moving north and the colder air moving south or southeast. So this is our cold front and this is our warm front. And you can see that the circulation around that is counterclockwise, so it's going in that direction. The low pressure center is often right in the middle. All right, so we had our stationary front, and then it starts to take on a wave shape. That's where one is starting to advance on the other. And then that causes a low pressure to be centered above that wave. We have counterclockwise, or this is also known as cyclonic circulation. The air is moving in a counterclockwise direction around this low pressure. This cold front is going to catch up to this warm front, and it's going to produce an occluded front where we have the warm sector being displaced aloft. The difference in pressure weakens, and now the fronts, there are no more fronts really. The air is kind of mixed together. All right. So the clouds that we would typically see with a mid-latitude cyclone as it's moving. All right, here's our low pressure. Here's our cold front. Here's our warm front. And this is already occluded a little bit. So that's why the low pressure is no longer right there at the kind of the vertex of the cold and the warm fronts. Okay, so what we're doing is we are looking at a line from F to G, or we can go the other way, G to F. Okay, I think that's a G. I'm sorry, I can't really see. But anyway, that represents this top picture. So if you were to drive from this to this, this is the progression of clouds that you would see. You would have some altostratus at this point. As you move, the clouds get a little bit lower. Okay, now you're in the occluded part right here. So you're going to get warm air aloft, and you're going to get some steady rainfall. As you move out of the occluded part, the clouds start to rise a little bit, maybe some cirrostratus and some cirrus up here. So we've gone from here to here. All right, let's go to a different part of the storm. So now we're going from E to A. Okay, so in letter E over here, somewhere on the border of Texas and Oklahoma, we're in a cold air mass because we're behind the cold front. So this is our continental polar air mass. And that's moving in this direction. It's moving into the warmer air mass. So right in front of the cold front is where we're going to see the most active weather. So back here at E, it's cold. It might be a little bit cloudy, but it's cold and dry, not a big deal. As we get closer to D, right in the transition between cold and warm, this is where our air has been shoved up, and we're going to get often cumulonimbus clouds and thunderstorms, possibly severe weather with that. All right, so now as you drive from D to C, it's fairly clear. You're in the warm sector of the storm. So now you're in this maritime tropical air mass. And so the clouds, it's going to be probably cloudy. And once you get to C and move from C to B to A, you start to see clouds and precipitation. But as you move away from that, the cloud deck is going to get higher, and the weather is going to clear a bit. So depending on where you are relative to this mid-latitude cyclone, you will have a certain kind of weather. Okay, as you know, air flows down the surface, but then all the way up as well. And so we have cyclones and anticyclones. Cyclones is what we just looked at, where these are the low pressure areas. And then we also have our high pressure areas. That's a really bad H, but I think you know what I mean. Okay, and these are often found next to each other. Now, in our cyclone, this is our low pressure area. At the surface, the air is coming together. So here we are at the surface. The air is converging. It's coming together. Now, when it comes together, it can't just pile up there. And it can't go down because you're at the surface. So the only place it can go is up. So when we have convergence, then we have rising air. Okay, and if you go aloft to maybe almost the top of the troposphere, up here, this air diverges. So once it gets up, then it's got to move outward from one another. So it's surface convergence, lifting, and then upper air divergence. Okay, so here's our high pressure at the surface, low pressure at the surface. You can see this is our mid-latitude cyclone. We have cyclonic flow moving in a counterclockwise direction, and air is rising in this. Now, when it hits the jet stream, it's going to be sheared off. Now here we have cyclonic flow. So air is now moving in an anti-cyclonic direction or clockwise. Okay, so it's moving around in this direction. And in high pressure areas, okay, we have air that is sinking toward the surface. Now, if we have air sinking, once it hits the surface, again, it cannot pile up there. It can't go back up right away. So the only place it can go is outward. So we have surface divergence. So we're moving like this at the surface. Now in the upper air regions, we have convergence. The air is coming together up here where the jet stream is. So it's coming together. Now it can't go up anymore because you're going to bump into the stratosphere. So the only place it has to go is down. And once you get down to the surface, it has to go somewhere, and the only place it can go is outward. Okay, let's talk about thunderstorms. Obviously, a thunderstorm is something that generates lightning and thunder. The features of a thunderstorm would be cumulonimbus clouds. Fun fact, maybe it's not really fun, but it is for me. I got a kitten about 3 years ago, and she was gray. Well, she is gray with flecks of beige in her. She's a dilute tortie, if you know what that is. And then right down the center of her forehead, she's got kind of a yellow streak. So I named her cumulonimbus because she looks like a cumulonimbus cloud. She's got the gray, she's got the little flashes of yellow or gold in there for the, kind of flashy lightning. And then she's got the lightning bolt right here. So that's my little cumulonimbus. I call her Q. I should have put a picture up here. I'm sorry I didn't do that. Okay, so with cumulonimbus clouds, you often get very heavy rainfall, and you can sometimes get hail with that. Now, cumulonimbus clouds, if this is the surface, okay, they have a pretty low base, but these are very, very, very tall clouds. They can reach the top of the troposphere. So this cloud can be, anywhere from 5 to 7 miles tall. It's really, really tall, okay? And sometimes if it's powerful enough, it can even penetrate into the stratosphere. Okay, in order to get cumulonimbus clouds, we need to have warm, moist air. So warm, moist air is our maritime tropical air mass. Okay, maritime tropical air masses are very unstable. And so we get rising air. So air rises, and as long as the air is warmer than the surrounding air, it's going to continue to rise until it's the same temperature as the air around it. Thunderstorms are extremely common. We have a lot here. They have some, everywhere has had a thunderstorm for the most part. Okay, so we're looking at the occurrence of lightning and thunderstorms, and these are lightning flashes per year. So we have the low frequency of lightning, mostly out over the oceans and right off the coastlines. And then we have the denser areas of lightning, where we get a lot of lightning and thunderstorms throughout the year. Central Africa, down here in the tropics, over here where we are. And then here are the days per year with thunderstorms. So if there's a thunderstorm someday, then that day is counted as a thunderstorm day. Right here, we are between 40 and 50 thunderstorm days per year. It increases the farther south you go, and that's because the air is normally warmer and moister, which would lead to more thunderstorm formation. You see, there's kind of a bullseye here in central Florida. This bullseye with 100 or more thunderstorm days per year can be caused from a couple different things. It can be caused from the competing sea breezes, where we have air coming in this way and air coming off the Gulf of Mexico here, and they kind of meet here in the middle, which is we have convergence, and so that's going to cause rising air. This bullseye can also be a product of hurricanes moving through, as one is moving through right now. You can clearly see where the Rocky Mountains are and how we see a difference here between the eastern, or most of the eastern part of the country, and the part west of the Rocky Mountains. They have very few thunderstorms out here, especially in California. I spent about a month in Los Angeles, and I joined a softball team while I was out there, and I was playing, and there was a very distant thunderstorm. So you could see kind of, you know, some flashes of lightning. It wasn't close at all. And we're used to that where we are in Indiana, but they're not used to that. And so we were playing, and I mean, people would miss catching the ball because they were like, oh my gosh, did you see that lightning? Wow, that's really cool. It's like, okay, that's really no big deal because I see that all the time. But out there, it's just not very common. Okay, so the different stages of a thunderstorm, we always need to have a continuous supply of warm air and moisture. Now each surge, so we have this rising air, okay? Each surge causes the air to go even higher. And eventually it starts to rain and the rain starts to fall. This is the most active, mature stage of the thunderstorm. In this stage, you would have gusty winds, frequent lightning. Sometimes you would get hail, very heavy precipitation. Now, as this rain falls through that warm air, it actually cools it a little bit. And so by cooling that air from the precipitation, that's going to cause the thunderstorm to die out. All right, so we can start off with just regular cumulus clouds that form because of surface heating. Okay, this air right above the surface gets warmer than the surrounding air, so it rises. So we get cumulus clouds being formed. Okay, now this dashed blue line indicates the freezing level. So this is the point in the atmosphere where the air is at 32 degrees Fahrenheit. So anything above this can freeze, okay? So the cumulus stage, we have updrafts and we're building these clouds. The mature phase is when we get heavy precipitation. Now we have updrafts in the red and downdrafts in the blue. Heavy precipitation, as this precipitation falls, it is cooling this air right here. And so that's going to kind of cut off this downdraft. So what we end up with is mostly sinking air, light rain. It's a little bit cooler at the surface. And you can always, you know, people talk about the weather all the time. If you have nothing else to talk about, you always have the weather to talk about. You know, you hear them say, boy, I can't believe that the temperature dropped 10 degrees in 30 minutes. Well, that was a cold front moving through, and it's cooler now also because of the rain-cooled air. Okay, how about tornadoes? Tornadoes are extremely violent windstorms. They are the most violent storms that we have anywhere on the earth. They often don't last very long. Sometimes, you know, they just kind of touch the ground and then go back up, but they can stay on the ground for several hundred miles. So they're just, it's a rotating column of air. Now the pressure inside a tornado is much, much lower than the air around it. So that's what causes air to rush into it, because I think you have learned in a previous chapter that if you have an area of low pressure right here, then air is going to try to move into that area to try to fill in that low pressure. Okay, same thing is happening inside the tornado. Okay, we're right here. Air is rushing in, and it now, as it's rushing in, it's converging, and it's rising, and it's spinning. The fastest winds on Earth occur inside tornadoes. Now, tornadoes, you cannot see them unless the air has condensed or it's picking up debris. So tornadoes would be invisible, but luckily, and I say luckily, it's just so that we can actually see them, it's picking up stuff, oops, so sorry. It's picking up stuff from whatever it's moving over, whether it's a cow or, but often it's just dust and dirt and that kind of stuff. And so that kind of gives you the black brownish tornadoes. The white tornadoes are pretty clean. It's just condensed water vapor. The US is a perfect breeding ground for tornadoes. We have a lot of tornadoes every year here. And here meaning the US. Okay, so here's our tornado. This is our funnel, and you can see the debris that it's picking up, and this debris gets incorporated into the entire cloud itself. This is the parent cloud that it's coming down from. So this is part of a larger cumulonimbus cloud. This part is the wall cloud that lowers right before a tornado actually forms. Tornadoes are associated with severe thunderstorms, and often these thunderstorms are of the supercell kind. So these supercells are enormous cumulonimbus clouds, not just enormously thick, but they cover, they're a really large storm in area. And in these supercells, let me draw our cumulonimbus again. Okay, here's the surface, here's our cumulonimbus cloud. What we get is a mesocyclone. So the mesocyclone means that through the center of this cloud, through the depth of it, we have a column of rotating air. Now, it's not rotating tightly enough like a tornado, but this whole thing is rotating. Okay. That is, you know, when they say, look up, and if you see rotation, then take shelter. That's what we're looking at. We're looking at the mesocyclone when we see rotation. What do we need for this? We need to have moisture available, because as the water vapor condenses back into a liquid, it releases latent heat. This latent heat associated with the phase change of water is really what drives, it's the energy source for our tornado. We also need wind shear. And wind shear is a change in wind speed and direction with height. Okay, so here we are at the surface again. Wind shear. So at the surface, we have a lot of things on the ground. We have houses, skyscrapers, trees, you know, whatever we've got. That's really a bad tree, I'm so sorry. So there's a lot of friction. So the wind speed at the surface is often low. But as we start to get above these obstacles, the wind speed increases. The wind picks up until there's no friction at all. So you can see that there's an increase in wind speed with height that causes this air to kind of curl under itself. Now the same thing, the same wind shear can happen with a change in direction. So maybe at the surface, we have a west wind, and then up a little bit, maybe we have a southwest wind, maybe a south wind. So it's turning. So it's not only increasing in speed, the higher up you go, it's also changing direction. And that again causes this air to kind of curl under itself. So what we're left with is this horizontal column of rotating air. Okay, so we're going like this. It's invisible, you can't see it, but it's doing this. All right, how do we get the mesocyclone formed? Well, you've got your cylinder of air doing this. Hey, here comes an updraft, okay? Now it picks it up and now it's spinning like this. Now we've got our vertical cylinder of rotating air. That's how the mesocyclone is formed. All right, tornadoes are often right ahead of the cold front because we've got the cold air undercutting that warm air, causing it to rise. With rising air, we can get clouds, condensation, and thunderstorms and tornadoes. Tornadoes happen most often during the spring months because in the spring months, we still have the colder, drier air from Canada that's still coming down, moving south. But the Gulf of Mexico has started to warm up a little bit. So that's going to kind of start to creep up. And it's where those two meet that we have the severe weather. Then in the summer, we can still get thunderstorms, but they may not be as severe because we don't have such a temperature difference. And we can get tornadoes here in the winter. I remember one early January, we had a tornado in Indiana. So couple of interesting facts about tornadoes. All 50 states have had a tornado at some point. That does include Hawaii and Alaska. And every single calendar day of the year has had a tornado recorded on it. So today is what, October 10th. On some October 8th. On some October 8th, somewhere in the US, there was a tornado. Same thing for the next day and the next day and the next day. So not necessarily every year, but on this day in some year, there was a tornado. So it can happen anytime, anywhere, given the right circumstances. Okay, so here is our wind shear. We've got the weaker winds at the surface, stronger winds aloft. This curls under and we get this horizontal column of air rotating. Now here's an updraft. It's going to pick that up and now this column of air is rotating vertically. This is going to cause air to be moved into it because we've got low pressure being formed right here. Wherever you've got rising air, you've got low pressure. And so air is going to be rushed into it. And if it tightens up enough, conservation of angular momentum says that it has to spin faster. And that's when you get the tornado. Conservation of angular momentum, if you've watched any figure skating, that's the perfect example of it. So the figure skater goes into a spin. What they do is they have their arms out like this, and as they want to spin faster, what do? They bring their arms in. They're decreasing their radius. They're making themselves smaller. When they make themselves smaller, they spin faster. And how do they stop? Increase your radius. put your arms back out, and that's going to slow you down. Same thing with this. So this is the tornado. We're spinning really fast, small radius, and then this is when it clears. All right, tornadoes in the US. Our graph is showing us the number of tornado days throughout the year for each month. So that's in the blue. So you can see that, they can happen any time of the year, but they are most likely to happen in the spring and early summer here. Okay, and this red line is the actual number of tornadoes. And I'm not sure which year this is for, but again, this peak lines up pretty well. And actually this is maybe shifted about a month earlier. So the peak here is right between May and June, but we can get tornadoes any time of the year. And we can get them any place in the US. Now, what I want to point out to you again is we've got another bullseye here in Florida. It's because you've got the opposing winds coming from the sea breezes, but also many of these tornadoes are spawned from hurricanes making landfall because the entire hurricane itself is spinning. And so when it gets to the land, it might spin off a tornado. But you can clearly see Tornado Alley right here with the bullseye in Oklahoma, another couple in Texas. So in through here, this is where we have that clash of those different air masses. We have the continental polar moving south from Canada, right here. We have the maritime tropical warm moist air moving in this direction, and the continental tropical air mass coming from Mexico here, and they all meet right about here. And so that's why we see Tornado Alley where it is. Look at us over here in Indiana. Did you know that Indiana is considered to be part of Tornado Alley? Illinois is not considered part of Tornado Alley, and neither is Iowa. But Indiana is, so it kind of skips over those states and then starts again with Indiana. We've got that little bullseye there. Nobody really knows why. I know that many, many years ago, there was a PhD student at IU who did his dissertation on, why we have this secondary maximum of tornadoes here in Indiana. 4 years of, classes and research and all that stuff. And basically his answer was, I don't know. I cannot figure it out. Nobody can really figure it out. I have some theories. If you look at where this bullseye is, you can see it's basically from Indianapolis northward. The northern half of the state was at one time covered in glaciers, so it's extremely flat. The southern part, where the glaciers did not actually get to, it's hillier and it's more forested. So there's a lot of flat plain area in northern Indiana, and so that could be a reason that we see more tornadoes there, because we need a large flat area in order to get that horizontal rotation going that's going to turn into a vertical rotation. Another theory is that maybe the winds coming off of the lakes have something to do with converging air. But again, it's not really clear why we're part of Tornado Alley, but nevertheless, we are. All right, the strongest winds anywhere on this planet, at least, are found in tornadoes, especially when tornadoes form at night, when a lot of people are sleeping. It can cause a lot of deaths because you're not monitoring the weather as much. You don't hear your cell phone go off or whatever telling you that there's a tornado in your area. Also, when a tornado hits an urban area, so it moves into a very dense, populated urban area, then that's going to do a lot of damage, and it's got a lot of people there, so there's a greater probability that it's going to cause loss of life. Most of these deaths are caused by debris that is flying. Now, fewer than 2% of the tornadoes in the US result in fatalities. This number used to be a lot higher because we didn't used to be able to forecast these tornadoes or to even give advance warning. But now we've got, sophisticated instruments like Doppler radar that can warn an area. It can give you maybe 5 to 7 minutes warning before a tornado hits, as opposed to 2 minutes. And those extra minutes make a difference to get yourself and your family and your pets and everything to a safe area. How do we measure tornadoes? We measure tornadoes using the Enhanced Fujita scale. That's the EF scale. Okay, here's the Enhanced Fujita intensity scale. It goes from EF0 to EF5, and we've got associated wind speeds with it. So let's look in miles per hour, because that's probably what you're more familiar with. With an EF0 tornado, the wind speed is anywhere from most likely 65 to 85 miles per hour. What kind of damage would you see with that? The damage would be pretty light. You might see some damage to your siding, maybe some shingles have been blown off, but it's not going to be too bad. EF1, the wind speed increases and the damage is moderate. So instead of just a couple of shingles, you've got considerable roof damage. You can have trees that have been uprooted, and this is going to turn over the mobile homes. Let's go up to an EF2, considerable damage here. Most mobile homes will be destroyed. This can shift homes that are built on a foundation, and the softwood trees can actually have their bark stripped from them. EF3 is severe, where the hardwood trees have their bark stripped off, and most houses are destroyed completely. EF4 is devastating, where you get just a complete flattening, complete destruction of really well-built houses. Schools have large sections that have been just completely just obliterated. And then the EF5, this is our most powerful type of tornado. You get incredible damage with this. There is just significant structural deformation of mid and high-rise buildings. Now, what I want you to remember is that the Enhanced Fujita scale for tornadoes is based on damage only. Damage only. The reason for that is because, as of yet, scientists have not been able to take any measurements inside the actual tornado. What happens is, once they get their instruments inside there, it's either the extremely low pressure or the wind speed just blows their instruments apart, so they don't get any readings. So they cannot directly measure the wind speed inside a tornado. What they do is, you've got a night where a storm has moved through and you've got damage. Somebody saw a tornado. Well, it's not confirmed until the next day, when scientists from the National Weather Service go out and they look at the damage. They want to see what kind of damage was done. They want to see if they can see a damage path, because often with tornadoes, you're going to get a narrow damage path. Once they say, okay, yeah, this was a tornado, Then they're going to assign an EF number to it. They're going to look at what kind of damage was done along that path. You know, did we have mobile homes completely turned over, or did we just have some shingles off of some houses? So based on the damage that they can see, they're going to say, well, all right, turned over some mobile homes. I see some flagpoles and some mailbox posts being bent. I'm going to say that in order to do that, the wind must have been blowing up to 110 miles per hour. So that becomes an EF1 tornado. So it is only based on the damage, not the actual wind speed. They're extrapolating what the wind speed must have been to do that type of damage. Okay. Now we still really cannot forecast tornadoes. There's no way to look at a 3-day outlook and say, we are going to have a tornado on the east side of Bloomington 3 days from now. Because they're extremely small in size and they don't last very long. So the computer models cannot predict that. They cannot generate those exact conditions to give us a forecast. But they do know when the conditions are right for a tornado to form. So they can say, okay, you know, 3 days from now, you know, we expect some severe weather and possible tornadoes. Okay, they know that much. They will issue a tornado watch when the conditions are favorable for tornadoes to form. Maybe a cold front is moving its way through with a large temperature gradient. You've got some wind shear. The air is very humid. So a tornado watch means that the conditions are favorable for a tornado to form. And they issue that for a certain area and for a given time period. Now, this does not mean that there's been a tornado spotted. It just means the conditions are right for it to happen. Now, a tornado warning is different. A tornado warning is issued when a qualified person has spotted a tornado, qualified meaning law enforcement or storm spotters, when they see a tornado, or if Doppler radar has indicated a tornado. So Doppler radar, instead of looking at you know, rainfall or clouds or thunderstorm activity, what we're looking at is wind direction. So if this is our radar site right here, what we would, I guess I do have colors here. Okay, just a moment. All right, what we see are, what we see is mostly green around this radar. And the green means that the air is moving toward the radar. And actually, so sorry, this part right here should be red. Okay. Red, green. Okay, now the red means that the air is moving away from the radar. All right, so in this case, this is not a big deal because we have air moving in one direction. Okay, so it's moving basically from the south to the north. And once it gets to the other side of the actual physical radar, then you see a red return. Now, what we don't want to see, if you don't like severe weather, is, you know, remember all this down here is green, okay? Because in all these areas, the air is moving toward the radar. And red. Okay, we might get a little pocket of red in here, okay? So when they see that, when the scientists see this, what we end up with is we've got this green area. It's moving toward the radar, sorry, this way. But right here, the red, it's moving away from the radar, like that. So you've got circulation happening right here. And that is a Doppler indicated tornado. They're seeing rotation. So it gets a little confusing because they will turn on the tornado sirens when there's a Doppler indicated tornado. This is good because it gives us a lot of lead time to get to safety. It's bad because people become immune to it. They think, oh, there's never a tornado when it goes off, so I'm not even going to worry. I'm just going to go outside and watch. And this is how many people are injured or killed because they're not taking it seriously enough. So if the sirens go off, you need to take cover. It does not always mean that a tornado has been spotted or that a tornado will form. But if it's a Doppler indicated tornado, then we've got that mesocyclone, we've got that rotation. And so there's a much greater likelihood that a tornado will form. All right, hurricanes. Hurricanes are formed over tropical oceans where the ocean water is extremely warm. And they're in very intense centers of low pressure. With that low pressure comes intense thunderstorm activity. Now, in a hurricane, there are no fronts. There's not a cold front and a warm front. It's all warm air. It's all warm, moist air. Okay, so with hurricanes, in order to be classified as a hurricane, the wind speed has to be blowing at least 74 miles per hour. This is sustained wind speeds. So it's not just a gust of 74 mile per hour wind. It is sustained. It is continually blowing at least 74 miles per hour. And that's a really stiff wind. Now, hurricanes can form anywhere between 5 degrees and 20 degrees latitude. And this can form all over the tropical oceans. This is both north and south, between 5 degrees and 20 degrees. They form, the reason that they can't form between 0 and 5 degrees is because the Coriolis force is not strong enough in that particular area. So remember, the Coriolis force is a deflection because the Earth is rotating, and there's just not enough spin to get the hurricane actually going at those latitudes. So it can't form right at the equator. It has to be a little bit away from the equator. It can't form generally above 20 degrees latitude because the water in the air is not warm enough to support a hurricane. Also, the hurricanes cannot cross the equator. So you can't have a hurricane that starts in the southern hemisphere and then crosses into the northern hemisphere. And the reason for this is because, one, it will kind of lose its spin as it gets closer to the equator. And number two, it would be spinning in the wrong direction. So everything is opposite in the southern hemisphere. Cyclones spin clockwise instead of counterclockwise. Same with hurricanes. Hurricanes in the northern hemisphere are low pressure, so they would spin counterclockwise, but in the southern hemisphere, they spin clockwise normally, so it would be rotating the wrong way. We call them hurricanes here when they form in the Caribbean or in the Atlantic Ocean. They're called typhoons when they form in the Western Pacific Ocean, and they're called cyclones in the Indian Ocean. So this type of cyclone that's really a hurricane in the Indian Ocean is different from those mid-latitude cyclones that we did earlier today. Australians call them willy willies. I don't know why, but instead of hurricane or typhoon or cyclone, it's a willy willy. Now the North Pacific has the greatest number of these storms per year, and those are in the form of typhoons or even super typhoons. All right, so now we're looking at when and where hurricanes form. So the red areas are the tropical oceans where we can see hurricanes forming. And hurricanes most often form, the ones that affect us in the US, form mainly August through October, right here in this area. And then these arrows indicate the direction or the path that they will take. Some will go ahead and move into, Texas and the Gulf Coast, and some will take a turn and move parallel to the East Coast. Okay, we've got another formation area right here, and then in the Southern Hemisphere, here is where the willy willies form that hit Australia. Time of year, this is for the Northern Hemisphere. Hurricane season is, I believe, from May through December. We need really warm water, warm ocean water down to a certain depth. It needs to be, I think, at least 83 degrees Fahrenheit down to a certain depth. And the months outside of this hurricane season the air is just not warm enough, the sun is not direct enough to heat up that water. But once that water starts to heat up, that's when we start to see the hurricanes. And so actually the hurricane season peaks in September, and then it slowly tapers off. All right, so remember that with the hurricane, we do have a low pressure center, which means that air is rushing in to it. And when air rushes in to fill this low pressure, it meets, it converges, and it has to rise. So we get rising air. We get intense convective activity. There's a lot of rising air, a lot of clouds. You get a wall of cumulonimbus clouds. Okay, this is where you can get really fast wind speeds and really heavy rainfall. Okay, so what about the eye of a hurricane? So a hurricane, let's see, can't draw today. Let's do it this way. There we go. Well, this is my hurricane, all right? Okay, here's the eye in the middle, and the winds are moving in this direction, counterclockwise. At the very center here, this is the eye of the hurricane. You may have heard that the eye of the hurricane is the worst part, but it's actually not the worst part of the storm. It's the calmest part of the storm. If you're in the eye of the storm, you're going to find low wind speeds, rain stops, it's warm, you have clear skies because air is descending, it's coming down from above, and it's the warmest part of the storm. Now the eye is not very wide, it's maybe only 12 or so miles in diameter, so it's going to cross over your area very quickly. So you don't want to think, oh wow, the hurricane's over, look at this is beautiful weather, because in about a few minutes you're going to get hit with actually the worst part of the storm. And the worst part of the storm is right on the edges of the eye, and that's called the eye wall. Okay, so let's look at, this is Super Typhoon Jangmi. So you have a well-developed eye right here in the center. And the more well-developed the eye is, the stronger the hurricane. So this is very well-developed. You can see that it's clear, or basically clear, or at least much clearer in the eye. Here are the outward rain bands. And then right around, and it's really hard to see here, but right around the eye is where we have the eye wall. It's a little bit whiter and brighter, and that's because of the intense convective activity. Hurricanes will form in all tropical waters except for the South Atlantic and the Eastern South Pacific. The energy comes from latent heat again. So it comes from water vapor that's condensing back into a liquid. When it does that, it releases all of this latent heat. Okay, we saw when hurricane season was. So what causes a hurricane to decay? All right, so a hurricane can diminish in intensity when any one of these three things happens. It can move over an area of colder ocean water. It can move on to land because, you know, it's really being fed from the very warm air, or sorry, the very warm water. So when it moves over the land area, its energy source is cut off. There's no longer any warm water there. So it starts to die out. Or if the large scale flow aloft, so up toward the jet stream, is unfavorable. Believe it or not, for a hurricane to form, we want to have calm or weak winds up aloft, because if they're too strong aloft, it's gonna blow the storm apart and it won't actually get to take hold. So there are different stages with hurricanes. The first is a tropical depression. A tropical depression is just an area of low pressure that develops over a tropical ocean. And in this, you know, the winds are, you know, it's windy. The winds are steady at about 38 miles per hour. Once those winds get to about 38 or 39 miles per hour, then it's called a tropical storm. Once it's called a tropical storm, then that's when it gets its name. All right. Let's look at the conditions inside a hurricane. So we've sliced this hurricane in half and we're looking at that. So here's the eye, and these red arrows indicate where the air is subsiding and warming up. So this is the clearing that you see if you're in the eye of the hurricane. But the eye wall are these blue lines right here. So this is where you have, excuse me, intense convection, cloud, cumulonimbus cloud formation, winds, and intense rainfall. We've got outflow at the top. So it's kind of like a vent where it's venting that air outward. And that's going to cause more air to be moved inward and go upward. Okay, so that's helping to pull the air up and out. And then we have our rain bands that spiral around the eye. This graph down here is showing the surface pressure and wind speed as a hurricane moves over, it's Cyclone Monty over Marty Station in Western Australia. All right, so here's the average wind speed for that day and time, and here's the pressure. So pressure and wind speed are often inversely proportional. So as the wind speed goes up, you can see that the pressure is dropping. So where the pressure is the lowest, the wind speed is the highest. Okay, when the wind speed, this is like right at the eye right here, okay? And you can see that the pressure starts to increase. And so this is the eye wall and this is the other eye wall right here. Okay, let's look at these sea surface temperatures. So these measurements are in degrees Celsius. I'm not sure what month this is, but I'm going to guess it's maybe around August or September. So the sea surface temperatures here are almost 28 degrees Celsius. And let's see if I can quickly do that in my head. What do we have? 24. So 82, 83, 84 degrees right in through here. And these waters are warm enough to support a hurricane or hurricane development. What kind of damage will we see with hurricanes? There are different factors that will determine how much damage there is. Of course, we have the strength of the storm. Also, the type of area that it affects. You know, is it a rural place? We don't have a lot of rural places on the coastline, but so the size and the population density of the area affected, and also the shape of the ocean floor near the shore, because you know, let's see. Oop. Well, I don't know why I'm not writing anymore. Okay. So if this is land here, well, that's really bad. Land and then ocean right here. The shape of this seafloor as you approach the land will determine the shape and the height of the waves, the intensity of the waves. Just waves in general, but that's amplified when you have a hurricane. How do we classify hurricanes? We use the Saffir-Simpson scale. This ranks the relative intensities of hurricanes. Now, remember when we talked about the enhanced Fujita scale, I said that tornadoes were classified based on the damage that was done. Hurricanes, even though they can do a lot of damage, their winds are usually much less, much slower than in a tornado. So we can actually measure the wind speed inside hurricanes. If you've ever watched the Weather Channel, you see some of the meteorologists standing there reporting in the middle of the hurricanes, and sometimes they'll take their belt and strap themselves to the posts of a balcony or something like that so they don't get blown away. All right. The part of the storm that does the most damage is the storm surge. What is the storm surge? Well, it's a large dome of water, very wide, maybe 40 to 50 miles wide, that sweeps across the coast whenever the eye makes landfall. And with the storm surge, you get a lot of flooding. So it's not necessarily the rainfall that's doing all of the flooding, but a lot of it is due to this storm surge. Now, what causes the storm surge? Got a couple different scenarios here. All right, so here's your beach house, which is really great, in the ocean. Now, when the pressure is low, as it is in a hurricane, that means that there's less force pushing down on the surface of the water. So that allows the surface of the water to rise up a little bit. Okay, also remember that in order for hurricanes to form and to be sustained, we have to have fairly warm water. So now we get some thermal expansion because this column, this part of the water is really warm, and so it's going to expand a little bit. So this thermal expansion combined with the low pressure causes the surface of the water to actually rise. So how does that cause a wall of water? Well, normally here you've got the waves breaking right about here, okay, on a regular day. Now, when you have a storm surge and the the surface of the water is higher, it's not gonna, the waves aren't gonna break until much farther inland. And all of this is a wall of water that's gonna make its way on shore. And so this is what does most of the damage. You also get wind damage, of course, especially if it's an extremely strong hurricane. The winds can blow really fast. And then inland flooding from the storm surge and from the rainfall. Let's look at the Saffir-Simpson scale. So category 1 hurricane is the least destructive. You might have a central pressure of about 980 millibars. The average surface pressure is about 1,013 millibars. That's what we call normal pressure. So it's a little bit lower, but not, I mean, you know, not really, really low. The wind has to be blowing at least 74 miles per hour, so converted into kilometers. And here's the storm surge. So this means that the surface of the water will be anywhere between 1.2 and 1.5 meters higher than it would normally be. And the damage is minimal. As we move up through the Saffir-Simpson scale, a category 2 hurricane has a lower central pressure. The winds are blowing faster, and we get a greater storm surge. And all of that leads to more damage. 3, 4, 5. Hurricane Katrina was a category 5. The central pressure for that is less than 920 millibars. That's a very, very low pressure. The winds can be greater than 250 kilometers per hour. Still not as high as what we would see in a strong tornado, but I mean, that's, you know, that's really fast. That's gonna do a lot of damage. And the storm surge in meters is over 5.4 meters. Now remember, a meter is about 3 feet. So we're talking about 16, 17 feet higher than normal. So this wall of water is going to go really far inland, and it's going to do a lot of damage. Moving water has an amazing force behind it. All right, so here's some destruction from the storm surge associated with a hurricane. You can see, I mean, things are just obliterated here. And if we look at the aerial view of it, I think that this house is this one. I don't know if it's in the same, I don't think it's the same angle that we're looking at, but you know, all of this is flooded here and even here because that water surface was coming in and flooding all of this area until finally the storm moved away. We can monitor hurricanes using satellites. They're looking at rotation in the open ocean. They can make estimates of the wind speed, and they're looking at cloud development. And then based on the upper air structure and flow pattern, they can predict the path of the hurricane. This path often changes, and it'll change naturally. You can't just change it with a Sharpie on a map, but it can change, and it will change because we still cannot control the weather. So they'll put out a forecast, and then a lot of times they will have to modify that forecast or where the track is. All right, thank you very much for hanging with me. I appreciate it. I have a good time teaching this stuff. It's really what I love. I hope you have a great rest of the semester. Thanks for joining me.